All right, hey everyone, I just want to go through and make a video answering the sample midterm 2. Let's get into it. So I need the limit as x goes to 0 of f of x. This is asking what y value do you approach as x approaches 0, and the answer is 5. And importantly, we mean what do you approach, right? So as x goes to -4, f approaches -3. It does not approach +2. I'm nowhere close to +2. Okay, the limit here is not +2. Okay, the limit is not the same thing as the function value. The limit's talking about what you approach. What are you getting closer to? All right, so what does the y value get closer to as the x value gets close to -2? Well, let's see. Here's -2, and as we get closer and closer, the y value approaches 1. No biggie, sweet. All right, so now we're going to approach 3, but how are we going to do it? Well, this little superscript negative is saying from the left, okay? 3 from the left. So if we approach 3 from the left, and I'm walking along my graph, then my y value is approaching -4. And that's it. But notice if they don't specify the direction for approaching 3, so there's no superscript minus, there's no superscript plus, then I don't know how to approach. Should I walk along this path? Should I walk along this path? And notice I get different answers. I'm either going to approach -5 or I'm going to approach -4. And because of that, we say the limit does not exist. Okay. All right. Now d dx of f, that is f prime. So we just want the derivative, and it's evaluated at x equals 0. So we want the derivative at 0. So we want the slope of our graph at x equals 0. So let's see. Well, that'd be right here. The slope is 0. If I was standing at the top of this hill and I was a really, really tiny person, it would feel like it was flat. So that slope is 0. All right, here we have another fancy way to talk about a derivative. So this is f prime at 5, and this here is just the actual definition for the derivative. I think it's chapter like 2.1 in the textbook or something like that. But okay, we want f prime of 5. Hey, here's 5, here's f of 5. So what's that slope? Well, it goes over 1 and up 1. This has slope 1, so there we are. All right, f prime at 6, or sorry, -6. Well, you know, if I was standing right here, gosh, I'd really have to maintain some balance. And if someone said, what's the slope under your feet? I'd say, I don't know. I'm at this weird corner thing. And yeah, the slope is not well defined. It just doesn't exist there, okay? All right, f double prime at 4. We're talking about the curvature at 4. Is it curved up? Is it curved down? Or is it not curved at all? And if we look at 4, boom, not curved at all. We are straight, so we're not curved at all. F double prime is 0. And just really quickly, if you had a linear function, mx plus b could be f of x, and you take one derivative, that'll tell you the slope. So f prime of x is m. If you take a second derivative, you get 0. And that's because lines aren't curved. So that's what that's saying. All right. On to the last one. So I need to take the derivative. This involves the chain rule. I have this outside function where I have a power 2 here. So I do the derivative of the outside. I leave the inside alone. And then I take the derivative of the inside. And, you know, we typically don't write a 1 exponent, and it gets it really confusing with prime. So here we go. 2 times f of x times f prime of x. All right, so if we want to plug in 0, then we should plug in 0 to all the x's. So this is 2 times 5, which was f of 0, times 0, which was f prime of 0. Remember, we just did that. So, in fact, here the answer is 0. All right, that's problem 1. Problem 2, compute the derivative. All right, so we need to use the fact that derivatives distribute. I'm going to try and show all my steps. This is way more than you would be expected to do, but I want you all to understand where this all comes from. Okay, derivatives distribute over sums. And in fact, numbers like 3, for example, you can sort of just worry about at the end. So I need the derivative of x to the 5th plus the derivative of x to the -3 plus the derivative of 10. And so we do the power rule here. The 5 comes down. 3 times 5 is 15. And you have x to the 4th. Plus the -3 comes down. And -3 minus 1 is -4. Be really careful. Don't do -2 here. Don't do it. Okay? Common mistake because people are so used to 3's becoming 2 and you subtract 1. But when it's a negative, you get more negative. All right, derivative of 10, that's 0. You don't have to write the plus 0. That's fine. And why is it 0? Well, you know, if you have the function y equals 10, there we go, y equals 10, and you're standing on it, and someone says, hey, what's the slope under your feet? You say, this is flat. This is a slope 0. Yeah, that's right. Another way to think of it is there's really an x to the 0 here, and if you do the power rule, that 0 comes down, and it kills everything. It makes it all 0. So there's many ways to think about that, but, oh, I didn't want to erase all of that. Sorry. Here we go. Boom. There we go. So here's the answer. You don't need to rewrite it or anything. That's all it is. All right. Hey, here's another letter, and it's not x. So just treat it like a number. Okay, they're just trying to trick you. Let's take that derivative. And, okay, I could show distributing the derivative across sums again, but I'm not going to. Let's just bring this 2 on down here. 2 comes down. I'll have 2sx minus, and then this is just 1 over s because the 1 came down, and then it was x to the 0, which is really just 1. So there it is. Here, there's no x's. It gets treated just like the 10 got treated. It's a 0. So in fact, there's the derivative, and we're done. All right, hey, look at this. It's a product. So I do the product rule, which, oh, by the way, that's right. What's the equation sheet you're going to be given? Hey, remember that time when I said we had this expression here, but this was a 5, and this was a 5, and I said it was f prime at 5. These things will literally be given to you on the test. And so if you see something you don't know, maybe a good approach would be check the formula sheet. Check if there's something like it on it, and then maybe there's some other version that you do know, right? So, all right, anyway, that's not for the question. So what is the question? Let's see. We need the derivative, and we need a product rule, and I just want to show you that the product rule is here. Where is it? Sum rule, stability theorem, derivatives. Oh, apparently we're going to be given sine and cosine. Okay, fine. Ah, right here. Here's the product rule. So if you have one function times another function, derivative the first times the second, derivative the second times the first. All right, so that's what we're going to do. So I need to compute the derivative of 2t, and then I'm going to multiply that by cosine of t. All right, and I need to multiply 2t times the derivative of cosine of t. Right, so who gets the derivative swaps, right? Derive the first function, derive the second, and just multiply the leftovers. All right, so first off, test-taking strategy, all right? I can't say this and emphasize enough. If you don't know how to take this derivative, but you see that there's a product, if you can get this far, that's worth something, okay? I guarantee instead of a 0, you'll get something for that. Maybe you get tricked here. Maybe you don't know what this derivative is. Well, it turns out it's the natural log of 2 times 2t. And so, all right, let's put down a little star. Something that maybe we should remember is if you want to take the derivative of some number to the power x, it's equal to the natural log of that number times the original function, a to the power x. And one way to see this is to actually write a to the x. A to the x is e to the natural log of a. Okay, this quantity here, that's a. It's just dressed up in a fancy costume. So then we're going to put it to the x power, and now it's a to the x. All right. But in this form, you could think of it as e to the natural log a times x. And this right here is a number. Natural log a is just a number. Okay, if it was 3 to the x, or gosh, if it was 2 to the x, then that would say natural log 2, which is 0.69 something, okay? Anyway, so this is definitely something worth remembering because I don't think it's on the formula sheet. All right, so here we go. We've done that derivative. So now I multiply it by cosine of t. Okay, I've done all of this now, plus 2t. And I need that derivative cosine. And hey, you know what? Remember, it's right here. It's right here, negative sign. All right, sweet. So times negative sine t. And I don't like having these two operators next to each other. So what I do is I put the negative sign in parentheses to sort of emphasize this is multiplication. It's a negative thing, whatever. So this is fine. Don't bother reducing it or anything at all. This is actually easier to grade because we can just glance at it and go, oh yeah, they did the product rule. All right, here I have a function inside a function. And if we hop over to our equation sheet, gosh, a function inside of a function, this is a chain rule, right? So we take the derivative of the outside, we leave the inside alone, and then we multiply by the derivative of the inside. So here we go. I need to take the derivative of the outside. So the derivative of sine is cosine, and I leave the inside alone, cosine, natural log t, times. And now I take the derivative of the inside. So this is the derivative of natural log, which is 1 over the thing inside. So if it's a t, it's a 1 over t. If it's an x, it's 1 over x. If it's a function, you got to use the chain rule. Okay. But anyway, I would also, that's not my answer, but I would put a star next to this. You should totally know some log derivatives. In fact, let me give you the more general one for a moment. If you, what do I mean by more general? Sorry. Here, I had any number I want to the power of x, right? So 3 to the power of x, 2 to the power of x, any number I want to the power of x, its derivative was the natural log of that number times, and then you have the original function. I could have just told you the e version, okay? So if you take the derivative of e to the x, it's e to the x, right? But this makes it look like you're not going to do anything. You are doing stuff. It's just that the natural log of e is 1, and so, you know, a pattern gets lost in this. So similarly, instead of talking about natural log, let's talk about log base b of x. And if you want to take the derivative of that, well, it's 1 over the natural log of b times x. Okay, so when it's natural log, then what would be here is a natural log of e, but that's just 1, so it goes away. And it's just the 1 over whatever's inside, so 1 over t. Here, I have a 1 over x, there it is, but I also have this 1 over ln of b. And again, like, that could be lost if b is equal to e. Sorry, that's a bit of a mouthful. Anyway, we've been done for a while. That's the answer to that one. I just want to remind you of some other popular derivative functions. I tell my students, sorry, actually, let's pause taking this for a moment. I'm just going to tell you all what I tell my students, which is there are 5 functions you should know. All right. So there's sine, which becomes cosine. There's cosine, which becomes minus sine. Sorry, these arrows are me taking the derivative. Okay, so sine of x becomes cosine of x. Cosine of x becomes sine of x. A to the x becomes natural log of a times a to the x. Log base b of x becomes 1 over the natural log of b, well, I guess I'll write it like this, times 1 over x. Okay, there's many ways to write it. I said 5 functions. Yes, and then the power rule. The power rule. These are the 5 derivatives that I think you should just totally memorize. Okay, just know these. And I could put all of this in a chain rule version. So chain rule version. So what happens if I take my sine function and I put a function inside of there? And then I want to take a derivative. Well, the derivative of sine is cosine. I leave the inside alone, and I multiply by the derivative of the inside. That's the chain rule. What happens if I do cosine, right? So I'm lazy, I'm writing c, but whatever, it's cosine. Take the derivative. Well, derivative cosine is minus sine. Leave the inside alone times the derivative of the inside. So this is f of x. Boom. Okay, a to the, and now I put a function up here. Oh my gosh, a function in the exponent. Well, the outside function, quote unquote, is a to the whatever. The derivative of that is a natural log of a times a to the whatever. And I leave that alone. Okay, then chain rule, derivative of the inside. So what is the whatever? In this case, it's f of x. All right, I could have log base b of whatever, f of x. Take the derivative, I have 1 over ln of b times 1 over f of x. That's the derivative of the natural log part. Sorry, not natural log. That's the derivative of the log base b part. But then I need to chain rule it times f prime of x. See, all of these, they all have this f prime of x because I'm just doing the chain rule. This is the chain rule version, right? Like, we need to drill that chain rule into our brains. Okay, the very last thing, I'm just going to squeeze it over here. Instead of x to the n, I have f of x to the n. I could have a cosine squared or, a natural log to the 14th power or whatever. What do? I let that n come down. I leave the inside alone, n minus 1. So that's the derivative of the outside times the derivative of the inside. So leave the inside alone. Boom. So, all right, there's the derivative of that. These are the 5 functions. If you're going to memorize any 5 derivatives, it's these 5, okay? Whew. All right, boom, here we go. Hey, look, if you just memorize that stuff, e to the function of whatever is the natural log of e times e to the whatever times f prime, the derivative of the whatever. This is the idea. This is me using what I just wrote where I had a to the f of x and I had ln of a to the f of x, f prime of x. If you rewind the video, you'll see it. All right, so this is the idea. This is the rule, the formula I'm going to use. Let's do it. I'm just, my f of x is x to the 1/2, that's the square root part, plus x. All right, so let's do this. So what's the derivative? The derivative of my j function is natural log of e. That's just 1. Forget about it. I have e to the root x plus x times, and now I have to do f prime. So I have to take the derivative of that. The 1/2 comes down, minus 1/2 plus 1. This is f prime. Okay, but the derivative I care about is this. Boom. All right, so if you just memorize those 5 functions that I told you about, then u prime of t is 1 over the natural log of 2. I take the base and I plug in the natural log, times 1 over t. Okay, so you'd be done. Okay, no work necessary. Now let's also just kind of look at this hint, use the inverse function rule. So what is the inverse function? You know, let's just take a peek. Let's see if, what's this? Okay, so the idea, where do I, all right, well, let's just play with this. So f inverse of x is log base 2 of x. Is that what we're looking at? Log base 2 of, and I just changed the t to an x. Fine. So this is the inverse of 2 to the x. Okay, the log undoes the exponential. All right, so here's my f. Now, let's plug the stuff in, all right? So my left-hand side is saying take the derivative of log base 2 of x. This is what I care about. This is what the question is asking about. Log base 2 of x, log base 2 of t, whatever. Okay, same. This is going to be equal to 1 over f prime. Well, I need to figure out f prime. But f of x is 2 to the x. So f prime is the natural log of 2 times 2 to the x. Okay, fine. So, but I don't want f prime of x. I want f prime of f inverse of x. So let's just take a moment and figure out f prime of f inverse of x. Well, f prime, that's natural log of 2 times 2 to the, and it used to be x, but it's not x anymore. It's now f inverse of x. F inverse of x is this monstrosity. Okay, so I do log base 2 of x. That was f inverse of x. And you could copy and paste this down here and you'll get full credit. But 2 to the log base 2 of whatever, so I'll put an x here, is the whatever. These two things undo each other. They are inverse functions. So these two things undo each other and you're left with natural log 2 times x. Okay, so that was the hint, but also notice, because the formula sheet had x's, I was using x's. This is t's, and yeah, we have 1 over natural log 2 times t. Like, that's what my answer was, right? So we got the same thing. It's just one's a t, one's an x. All right, last question on this page. N prime of x is, and now look, this is some function of x. This is an unknown differential function of x. Ugh, sorry I mumbled so much. And I have a function divided by another function. That's called a quotient in the math biz. And what do you know? Look at this. We got a function divided by another function. We got a formula to follow on a formula sheet. It's called the quotient rule. Let's do it. You take the derivative of the top, you multiply it by the bottom, then you take the derivative of the bottom, which in this case is still e to the x, and you just have to remember you're going to subtract the derivative of the bottom times the top, so times p of x, all over the bottom squared, e to the x squared. Full credit, no need to do anything else, you're done. All right. Oh, I gotta finish soon. Okay, right, great. Hey, L of x, gosh, if only there was a formula sheet where there was something labeled L of x, right there, and then just something to follow, right? Oh man, so we have this a, f prime of a, x minus a. All right, let's do it. So let's just remind ourselves what that formula sheet said. It said f of a plus f prime of a, x minus a. Boom. Oh my goodness, they tell us a. So we already know we want the function at -2. Oh, but gosh, our function's name is h. Let's go ahead and rewrite this using h. I want h of a plus h prime of a times x minus a. Okay, we can do this because we also know that a is -2. I want h of -2 plus h prime of -2, x minus -2. Whew. Oh my goodness. Okay, so what is h of negative 2? It is negative 1. All right, so I have negative 1 plus, what's h prime of negative 2? It's 3. Okay, 3x plus 2. Here is L of x. All right. Use L of x to approximate h of blah blah. All right, fine, just plug it in. So L of negative 2.25 is approximately h of negative 2.25. He never told us h, right? I have no idea what h of x is. But I know what L of x is. L of x is this. So let's plug in 2.25. This is minus 1 plus 3 times, negative 2.25. Well, if I plug in a negative 2.25 and then I add 2, that'll kill that 2. I'm just left with a negative 0.25. Okay, so this is minus 1 minus 3/4. Okay, so that's 4. That's minus 7/4. Okay, fine, whatever. This would be full credit, by the way. Like, there's no reason you'd have to simplify further. You got it? All right, so let's, including the graph of L of x. All right, let's go ahead and graph L of x. So it goes through the point negative 2 comma negative 1. Negative 2, negative 1, it's about there. And it has slope positive 3, right? It has slope positive 3. So, oh gosh, if I go over 1, I should go up 1, 2, 3. All right, so I want to go through these 2 points. Boom, I'm going to use the fact that I have technology at my fingertips, but I'm not going to use it well, apparently. Let's try this again. Shapes, click it, move it, bop it, twist it. Okay, all right, there we are. Great, and let's go ahead and label this. This is L of x. Okay, oh, hey, it told us to label h of x and L of x. Great. All right, and this spot right here is very important because we know that h of minus 2 is minus 1, but also L of minus 2 is minus 1. They have to agree, okay? They have to agree at this spot because this is the point of tangency. All right? This is that special spot where if I just kept zooming in, then my function and my tangent line would look the same. My function and my tangent line would look the same. So when I draw h of x, I definitely shouldn't be doing this and say h of x. Oh, God, if I had the ability to give a 0 on this entire question for that, I totally would. Because there's no way you can zoom in and say the green and the black line look the same. Okay, ridiculous. Absolutely ridiculous. The point of a tangent line is that it looks like your graph when you zoom in. So, okay, you could do something like this. Boom. And now, yeah, I have some bad penmanship, but hopefully you see what I'm going for. Let me try it again. I'm going to come in, and I want these two things to look the same, and then they don't have to look the same. But now, aha, they look the same here, right? That's the whole point of a tangent line. Let's see, did I do this right? No, because, I need the second derivative negative. That means I need h to be concave down. It needs to look like this, okay? So, all right, so instead, let's just go through this point and be concave down. So how about I come in like this, and I want to be tangent, and go away. Great. Here's h of x. At this spot here, I'm concave down. And notice in this little window here, the green and the black lines look the same. So that means, like, yes, this is tangent. Okay, this is what we're looking for, right? Sweet. And notice if you are at negative 2.25, maybe that's right there, negative 2.25, then because the black line is tangent to the green curve at negative 2, they have to be like pretty close to each other when you're near negative 2. And that was what was going on previously. H of negative 2.25 is approximately L of negative 2.25, okay? Because L is a tangent line. All right, whatever. We've done this. We labeled it. We have the correct concavity. Everything's looking good. Label your approximation part B is an overestimate or underestimate. Okay, so based on what I've drawn here, the black line lies above. We got black above green. And so that means the black line, my L of x, L of minus 2.25, is bigger or equal to h of minus 2.25. It is an overestimate, okay, based on this picture that I've drawn here. Okay, sweet. Next question. All right, a population in thousands changed according to, hey, this here is an updating function. And, oh, we want to write the updating function as f of x equals. Okay, fine. So my updating function, what does it do to its input? Well, here, the input, it's called p sub t. But what happens if you just call it x? Well, gosh, I guess you raise it to the fourth power and multiply it by 2. You cube it, and you multiply by 8. You're going to subtract those. Let's see. You'd square it, and you multiply 10. You add that. You'd multiply by 3 and subtract that. That's all we're looking for. That is, oh, sorry, then compute the derivative. Correction, that's the first part of what we're looking for. This is the updating function when you write it as a function of x. Okay, you just swap the variable name for x. So in this case, it was p sub t. Fine. Okay, f prime of x, the 4 comes down, I get 8x cubed. The 3 comes down, I get 24x squared. The 2 comes down, I get 20x. And the x is gone, I have 3. All right. Use the stability theorem to classify each equilibrium points. Whew. Okay, there's 3 of them. Let's take a peek. So p star equals 0. What do we have? Well, we need to look at f prime at 0. So we're going to look at the slope of the tangent line at 0. But specifically, what we really care about is the absolute value of that slope. How steep is it? I don't care if it's going uphill or downhill. I just care how steep is it. So let's find out. So this is the absolute value of, and if I plug in 0, that's 0, that's 0, that's 0, I get absolute value minus 3. That is 3, which, fun fact about 3, it's bigger than 1. Since this is steeper than 1, it's steeper than 1, this spot is unstable. All right, let's look at p star is equal to 1. So now I have to do f prime at 1, but I don't care whether I'm going uphill or downhill. I just care how steep I am. So we need the absolute value. All right. So what do? We do the absolute value. If I plug in 1, plug in 1, plug in 1, this is 8 minus 24 plus 20 minus 3. And if you work it all out, oh gosh, that's negative 7 and 8. This is 1. This is inconclusive. Inconclusive. All right, you need to either be bigger than 1 to talk about unstable or less than 1 to talk about stable. But if you equal 1, you're inconclusive. All right, p star is 2. So when you look at f prime at 2, let's specifically its absolute value. What do we get? 2 cubed is 8, so I have 64. Minus 2 squared is 4. That's 80, 90, yeah, 96. Okay, fine. And then 20 times 4 is 80. And then minus 3 in absolute value. Okay, let's see. These two things is minus 16. Is that how I want to do this? I don't know. Minus 9. Oh my gosh, this thing looks huge. Do I even trust it? Do I trust that I did this right? If I plug in 2, is this right? Is this right? Let's see. We have a 4. That's 80. And then 16 more is 96. I agree. And that's 80. Uh-huh. Okay, do I agree with this one? Yeah, that's 8 times 8. Okay, this thing is huge. It's definitely bigger than 1. Let's actually figure out the number, though. So apparently all of this is minus 19, yes. And if I add 19 here, if I subtract 19 from 64, that is 45. This is 45. That's bigger than 1. This is unstable. So we got unstable, inconclusive, and unstable. All right, last question, I think, or last dish. Okay, compute j prime. Sweet. The 1/3 comes down. 12 times a third is 4. X, a third minus 1 is minus 2/3. Okay, and then we have a minus 1. This right here is j prime of x. Sweet. X equals 0 is a critical number. Explain why. Well, let's write j prime of x in a different form. Because there's this negative exponent on x, that means x is actually sitting down here in the denominator. And now notice, if you plug in 0, that means you're dividing by 0. You can't divide by 0. So in a sentence, you can't divide by 0. Divide by 0. That works. Okay, you would get full credit for that. So I'm just going to leave it at that. Let's see. 8 and negative 8 are also critical numbers. Explain why. Well, it's simply because j prime of x. Oh, critical number. Sorry. So j prime of x is undefined. Okay, I suspect if you just said j prime of x is undefined, that'd be full credit. This explains why j prime of x is undefined, so I think it's a little bit more thorough, but I suspect this would be full credit. Here, if I look at plus or minus 8 and I plug it into j prime, I'm going to get 0. Okay, you could try. You could plug them in. You're going to get 0. The cube root of 8 is 2, and then we square it, we get 4. 4 divided by 4 is 1. Take away 1, you get 0. Use the first derivative test. So what we're going to do, we mark on a number line all the spots where j prime of x is 0, or undefined. Whoop, right there, okay? So now what we care about is whether j prime of x is positive or negative, okay? And the only way, all right, if I'm going to go from something positive to something negative, I either have to touch 0 or I have to jump, okay? And essentially, that's why. So now that we've marked all the spots where j prime is 0 or undefined, these are all the spots where you might jump or where you might hit 0. So now we need to investigate these regions, okay? The regions between the spots and to the sides of the spots. So this region over here represents all the numbers less than -8. All the numbers less than -8. Let's remind ourselves what j prime is. J prime of x is 4 over x to the 2/3 minus 1. If you plug in a super duper big negative number here, sorry, let me actually rewrite this in a way that really emphasizes what's happening. Okay, now if you plug in a super big negative number, negative that, okay? Well, we're squaring it, all right? Yeah, you take the cube root, but you're squaring it. So this thing here is positive. And in fact, it's a tiny positive number because we're making the denominator get really big. 4 over something really big is something really small. So a small number, -1, is a negative number. So over here, j prime is negative, which means j, the original function, is going downhill. Okay? Oh, sorry, not less than 1, less than 0. J prime is negative. What about in between? What about in between? Pick a number and plug it in. Let's plug in -1. If I plug in -1, the cube root of -1 is -1. And if I square it, it's +1. 4 divided by 1 is 4. And you subtract 1 is 3. That's positive. So you're going uphill. Plug in +1, you're still going to go uphill. Sorry. You're still going to be positive. You're still going to go uphill. Plug in something big, and it's just like plugging in a big negative. You're going to be negative. You're going to come downhill. So what do we find? This right here is a min. Okay, -8 is a min. +8 is a max. And 0 is neither. Okay? So this little sketch should get you full credit. You could say neither here. First year, yeah. So this all seems fine. Did you classify each? Yes, I would argue this is very clear, right? We can see the minimum is at -8, 0 is neither, and 8 is a maximum. But you could also just make a list. You could say like x equals -8 is a min. Blah, 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 is neither, is a max. Okay, anyway. All right, so now we want to find the absolute minima maxima on this domain. So absolute minima maxima, they're easier, okay? So let's make a list of our critical numbers. There was -8, 0, and 8. And let's make a list of our endpoints, -1 and 27. And notice -8, that lies to the left of -1, so we don't even care about it. It's not in our interval, so just get rid of it. So we have these 4 numbers, 0, -1, 8, 27. Each of those 4 numbers you should plug into j. We need to figure out j of 0, j of -1, j of 8, and j of 27. And so let's do that. If I plug in 0, I get 0. If I plug in -1, the cube root of -1 is -1. I'd have -12 plus 1, that's -11. Okay, if I plug in 8, the cube root of 8 is 2. That's 24 minus 8 is 16. And if I plug in 27, the cube root of 27 is 3. That'll give me 36 minus 3 is 33. Okay, well, right here, we have our absolute max. And right here, we have our absolute min. And we're done. Okay? So that's it.